Hi there everyone and welcome to my Cosmic Ray series. So I'm really happy today. After some waiting, I finally got my Cosmic Ray Muon Detector from the Muon Hunter project at www.muonhunter.com. Check them out, it's a really cool project and I'd like to show you the detector that I got from them and how it works and maybe some basic experiments. So this is the basic kit that you can order at muonhunter.com. You have some options, however, like you can order it with or without the Geiger tubes. They sell them to really fair prices. It's like what the market says, basically. I didn't use these because I had a lot of these laying around. But this kit, without the tubes, you get for around $100, €100, which is really fair. It's a great price for what you get. And so let's show you the components. You get the tube holders, of course, to put your Geiger tubes inside. And there's a little motherboard here. Stay here. Of course, there's a microcontroller. It's like a micro computer that goes on the motherboard. And the screen. That's what you get in the kit. And the cables, of course, for the Geiger tubes. However, you have a lot of options to modify the kit, or for example, you can put a Raspberry Pi onto it for logging and even to control a camera. That's an experiment for the future. I don't have my camera yet, but you could use this in combination with the cloud chamber to make pictures of muons going through the cloud chamber. I mean, how awesome is that? And also, what's really cool, the holders here, they're Lego compatible. They have Lego holes. So you can actually build yourself like a little Lego construction to stack them on top of each other and even like to put stuff in between or so, but I'll show you that later. So this is the assembled kit while it's working. What you won't get with the kit is the power supply, but it's USB, so you can use any phone charger or just your laptop or external battery, whatever. And also the Legos themselves are not included, and that's a pity, but I mean, I'm sure you have some Legos lying around at home. And this here is actually the idea about the Legos. You can make a stack to put the tubes on top of each other. Because what we're doing here is measuring muons that come fly through both tubes. They like penetrate both tubes at almost the same time, and that's why the processor here can figure out that it's a muon and not just any random background radiation. You can also put them sideways, for example, to see if any muons come from this direction, which is less likely, but there is a few. Before I want to go more in detail here, I want to talk about cosmic rays in general for a moment. So the phenomena called cosmic rays is basically, I like to put it in this way, mega radioactivity from outer space. Well, that's not technically 100% correct, but it sounds really cool. The thing is, it's actually the same stuff you get in radioactivity. You have alpha particles, you have protons, you have electrons whizzing around. The main difference is that the cosmic ray ones, they're much more powerful than your natural radioactive decay products like alpha particles. I talked about this in one of my older videos where it's about velocity, like speed of matter makes a big deal there. Like that what makes radioactivity dangerous. It's the speed of those particles, because they travel at 10 to 20% light speed, like alpha particles or beta particles from radioactive decay. However, in cosmic rays, these particles travel like in unimaginable high speeds. They can reach 99.99999 and something percent the speed of light. Like that's extremely fast for matter. Remember, we're talking about matter here. It's not light, it's not photons. So cosmic rays originate in really violent, huge astronomical phenomena like supernova, or in active galactic nuclei, like the cores of active galaxies, where there's a lot of forces and gravity involved, that can spit out these particles at these fast speeds. But that's the difference between the radioactivity particles and these, is in the radioactive materials like uranium or thorium, this is a process that happens inside of the atom. But here, this could be any random protons or nuclear cores whizzing around, just getting sped up really fast. Also, there are some theories that dark matter could be involved in these cosmic rays, but I didn't really research that good enough to tell you more about that yet. As mentioned before, they are composed of mainly protons. You get about 9%-ish, these percent numbers aren't really correct, 9% alpha particles, which are helium cores, that means 2 protons and 2 neutrons. Then you get some electrons as well, as your classical beta radiation. And you have 1% of these HZE ions. These are actually quite heavy atomic cores. They can go up to iron, I think. So the heaviest cosmic rays, primary cosmic rays, could be even like iron cores. You also get some positrons or antiprotons, very little, but there are some antimatter particles involved as well. However, they didn't really find anything heavier than an antiproton. Like there weren't any anti-alpha particles when they did a research on that. And in terms of energy, these processes that happen every day in our skies, all the time above our heads, quite a lot, they can give out as much as like 40 million times more power than the LHC. The particle collisions happen at 40 million times the power than they happen in the LHC, Large Hadron Collider at CERN. That's amazing. That's a lot of energy we're talking about there. There are even some calculations that say that the more higher energy primary cosmic rays, they can reach kinetic energies of, compared to if you throw a baseball with 90 kilometers per hour. But this power is all, you have to imagine it's concentrated to one atom or even less. So that's amazing. And of course the speed that they travel, that's the most amazing thing. It can be 99% light speed or even higher. There are some that will travel slower, but there's a lot that are in this speed range. And remember, it's matter, it's stuff. This is really insane that it can go so fast. It's awesome, fascinating. So let's get into primary and secondary cosmic rays. The point is, your primary cosmic ray, it's crashing into the Earth's atmosphere here with 99% light speed. The chance is quite high that it will hit some atom or some molecule in the air, quite high up, and that will create a cascade, like a particle shower, like an explosion basically. And these secondary particles, they will travel down to Earth at almost the same speed that the primary one hit, because there's so much energy involved. This is just, you'll get a huge particle shower. However, this is just symbolic. The angle, as it spreads, will stay quite narrow. I think it's only around 1 degree of deflection. So let's look at these particle showers for a moment. As we've seen before, the primary cosmic ray comes crashing into the atmosphere, hits an atom, and it splits up into, in the first place, into pions mostly. There will also be some neutrons and some protons being kicked out of the atom that got smashed. Then we have some neutral pions which decay to gamma rays. Then we have positive and negative pions, and they will decay to muons. There's also anti-muons, like positive muons. Mostly they have a minus charge, but you could get both. I think most of them are minus though. And then these muons, they're quite special particles. They're exotic matter, so they're unstable. They decay after a while, but they have quite a lot of mass actually. It's like an electron, but around 200 times heavier than an electron. And they have the ability, because they still have this high speed from the primary collision here, they're still traveling at more than 90% speed of light, and they will hit the ground, most of them. And also a neutrino will be emitted by this process. The interesting thing, however, is here you can test Einstein's theory of relativity, because we know a muon decays after 2.2 microseconds, I think. It's on the next sheet coming up. And if you calculate that to 90 or 99% speed of light, that would actually mean that it only could travel about 500 meters in the air before it decays. However, we can measure them here on Earth. They hit all the time, so something's going on there. What's happening is, because they are traveling so fast, those 2.2 microseconds happen much slower for the muon than for us. And that's why it's actually able to pass distances of 15 kilometers, say, compared to the 500 meters that it actually should be able to pass before it decays. But they hit all the time. We can measure them with the detector. That's, yeah, what it's all about. So muons are these weird exotic particles. They are unstable, as we said. They have a lifetime of 2.2 microseconds. They decay to an electron and two neutrinos most of the time. And the mass is 207 electrons. So they're really interesting, and that's the point is, like, most of the secondary cosmic rays that we can get here on the surface of the Earth will be muons. There will be some gamma rays, there will maybe be some other weird stuff, but we will also see how to filter out gamma rays with our detector. Let's take a look at the detector again. So some really basic experiments you can do first is measure muons vertically, because you will get more from straight up, because there's just less air that they have to pass. So they have a better chance to really making it down to the surface. You will need some patience. It's good to measure for long times just to get a good average. And then you can just flip the detector around and start measuring again, and then you'll get like the horizontal muons. Or you can play with angles. You can like look what comes from 45 degrees, or you could even build something with Lego to move this. That's really cool. One thing I did quite early on was to get myself a little bit of lead. I did a little bit of lead casting here out of old, fishing weights. Because the point is, I was thinking the tubes are sensitive to gamma rays, so maybe there could be some gamma rays that make it through both tubes. And we don't want that, we only want muons. So let's put it here with the Lego construction. This is great. Stick it in between both tubes. So now the lead should absorb most of all gamma rays that try to go through here. However, those muons, they have so much power, they will easily slice through the piece of lead. And that's how we can filter out gamma rays, basically. So I don't have like the digital logging working yet, but you have this screen here which actually gives you all the data, and for now I'm just analog logging, but I'll spare you with my messy notes. This is like just the results that I got. If I placed it vertical without lead, I got 1.2111 muons per minute. With the lead, I got 0.95. That's like really a difference, so something's happening there. Also horizontally, I have like, with no lead, I have like 0.1 muons per minute. It's less than 10% of the vertical measurement. But that makes sense, because they have to travel through so much more atmosphere. And yeah, I think that makes sense. It just proves to me that the device works. Also, I put it underneath a 20-liter water tank for quite some hours. And I have a little bit more muons from the reference count without the water tank. So I think the water is absorbing a very little bit. Not sure about that though. So yeah, you'll need some patience and just like good ideas where to put it, to measure, whatever. But I still have some good ideas for future videos. So stay tuned. So one last thing I want to show you before I end is that you can also use different Geiger tubes. Like these are the SPM20s, the ones that come with the kit. But I thought like, what if you put bigger tubes? You'll have a higher count rate probably, and that is really the case. So I got these SI22G Soviet Geiger Miller tubes, and I just had to add a little resistor here. I think it's 1 mega ohm, but it works plug and play with the kit, and that's really great. And it does give me a really higher count rate. I had 1.5 to 2 muons per minute with the small tubes in this setup. But this setup gives me about 10 muons per minute. That's really cool. The high pitch noise is just if a single tube fires, and the low pitch noise will be a muon when both fire at the same time. Come on. Where are the muons? No muons? Come on, where are you? Always when you need them, they're not here. Ah, there we go. Sometimes I have the feeling they come in groups. That's really weird. No idea why. So yeah, that's my first Cosmic Ray video. Hope you enjoyed. And stay tuned, there's more to come. See you soon, bye.